Welcome to this video on adding and subtracting waveforms. In this video we're going to look at two waveforms, and these waveforms are two voltages, two AC voltages that take the form of sine waves. So down the left hand side you'll notice the first column here is marked degrees, and I've gone from 0 all the way down to 360 degrees, going up in 10 degrees at a time. And my first column here represents my first waveform. It's a sine wave, and you'll see these values here increase from 0 to 10, all the way down back to 0 at 180 degrees, and then down to minus 10, and finally back to 0 again for 360 degrees. And we see that represented here by our waveform in the graph to the right hand side here. We've got a voltage that starts at 0, it increases up to an amplitude of 10, back to 0 at 180 degrees, down to minus 10, and then back to 0 again. If I have a look at the formula for this waveform, 10 sine omega t, in this case the 10 represents the amplitude of the sine wave, in that it goes up to a maximum of 10 and down to a minima of minus 10. The omega t, omega representing the angular frequency, but omega t in this case is representing the degrees here, going from 0 down to 360 degrees here. My second formula here is for V2, and we'll notice a couple of different things about V2 compared to V1. First of all, V2 has only an amplitude of 5 sine omega t. But we'll also notice that we have an extra term inside our formula here, omega t minus pi over 6. And this second term represents what's called a phase shift. Now at the minute, this is in radians, pi over 6 radians. Now pi over 6 radians is the same as 30 degrees. So we have a minus 30 degree phase shift. Well, what does that mean in terms of our diagram here? If we have a look to the right hand side, I've typed out a couple of things here, and we can see here that a negative phase shift, which is the case we have here, we have minus 30 degrees, a negative phase shift shifts our waveform to the right. If I had a positive phase shift, say plus pi over 6, plus 30 degrees, I would have a waveform shifted to the left. Let's extend our diagram here to include V2 as well as V1, and now we have both waveforms represented on our graph. If you look on the graph, first of all, you'll see that the amplitude is only 5, and so the maximum is 5, and we go down to minus 5. But you'll also notice that we have this shift to the right, and the shift is by 30 degrees. If you look carefully on the scale of the diagram here, what we should find is that a sine wave starts at 0, it reaches the center point or back to 0 at 180 degrees, and then finishes at 360 degrees. The easiest place probably to look is that center point, 180 degrees. We'll notice that our second waveform only crosses the axis 30 degrees later. So in this case, 210 degrees is where it crosses the axis. The whole waveform has been shifted to the right of where it should be. What we're going to do in this video is look at what happens when we add and subtract these waveforms from each other. And the way we do that, you'll notice I have all the instantaneous values of my waveform in these columns here. So for instance, at 0 degrees, my first waveform V1 has a value of 0, and we'll see that reflected on our diagram here. And likewise, V2 has a value of minus 2.5, and so there it is marked on my diagram as well. And what you'll find is that for my third column, V1 plus V2, both instantaneous values at any given point are added together to give a total. Now in this case, 0 plus minus 2.5 gives me minus 2.5, and so my third waveform that I'm going to add on my diagram in just a second is the sum of the instantaneous values of the two separate waveforms, and we'll see that repeated all the way down at any given point we just add the two instantaneous values to give our third. So let's extend our diagram again and include our third waveform, V1 plus V2. So we see that represented by the grey line here. And now we have the sum of the two waveforms. What we can also do is subtract the waveforms from one another. Again, V1 minus V2 at any given point gives me the subtracted result, and that's going to be my last graph that I'm going to include in my diagram here. Let's take the value at 90 degrees. V1 at that point is 10, V2 is 4.3, and so V1 minus V2 gives me 5.7. And so by including finally a fourth waveform on my graph, I now have the difference of V1 and V2, V1 minus V2, which is giving me this fourth trace, this yellow trace here. This is very easy to do in Microsoft Excel, but it's also easy to do by hand or using a table or similar. So now that we've produced two new waveforms on our graph, V1 plus V2, which is represented by the grey trace on our graph, and V1 minus V2, represented by the yellow trace on our graph, we can determine some of the properties of these two new waveforms and use these to come up with two formulas that represent these waveforms, much like the two formulas that we started out with here for V1 and V2. We can come up with a formula for V1 plus V2 and a formula for V1 minus V2. We started out by working in radians, but we said that we could convert radians to degrees. We said that pi over 6 radians is the same as 30 degrees. So let's work in degrees here, and we'll change that to minus 30. This is the same thing really, but it's easier to work in degrees than it is in radians here. And so looking at our graph, we have our first new plot here, the grey plot, and we see that our waveform goes up to a maximum point here of around, well, it tells us there in the little caption, 14.5. So our amplitude for this waveform is around 14.5, and we'll see that it goes down to minus 14.5. We also spoke earlier about this idea of the phase shift, and if a waveform's been shifted to the left, it's a positive phase shift, and if it's been shifted to the right, it's a negative phase shift. And we can see here, hopefully, this grey trace here has been shifted to the right slightly. We said before that a sine wave should start at 0, cross the midpoint at 180 degrees, and then back to 360 degrees at the end here. But our grey trace here starts slightly later. It crosses the midpoint slightly later, 10 degrees later actually. And so because it's been shifted to the right, we can say that it's a negative phase shift of 10 degrees. So in here, let's type our formula for our new waveform. In this case, we said it has an amplitude of 14.5. It's still a sine wave. So 14.5 sine omega t minus 10. So that's our new formula there for V1 plus V2. Let's apply the same method to V1 minus V2, our yellow trace here. We can see here that the yellow trace reaches an amplitude of around 6.2, looking at the caption there. And likewise, we get to a minimum of around minus 6.2. So that's going to be our amplitude, 6.2. But again, looking at the phase shift here, and again, it's easier to see it at the center point here, we can see that in this case, there's a shift to the left. And that shift to the left is a little bit difficult to read on this scale here, but it's just over 20 degrees. If our little scale markings there are every 10 degrees, we can see that it's just over 1, 2 and a bit. I'm going to make a rough guess there that that's about 23 degrees to the left. And because it's to the left, it's a positive phase shift. So we can approximate here, but we can say that our waveform has a formula of 6.2 sine omega t plus 23 to be approximate there. And that's our formula for V1 minus V2. So I hope this video has been useful. First of all, to show how we can plot sine waves and either add them together or subtract them from one another. But more importantly, to be able to look at these new sine waves and interpret some of their properties and determine the formulas that represent them as well.